So after learning what NDT was, now we want to look at what kind of materials we're going to be testing and why we have different methods based on what those materials are. So the first thing is when you're testing, when you're performing non-destructive testing or when you're performing NDI or NDE, and I didn't really get too much in the details. They said NDI, NDT, NDE are pretty interchangeable. The difference there that you'll see often have non-destructive testing is performing the test itself. NDE, non-destructive, or NDI, non-destructive inspection, kind of in that same category. Non-destructive testing, non-destructive inspection are both kind of looking at, finding the flaws. So they're very interchangeable. NDE, non-destructive evaluation, that is taking what you find, what you observe, or what your results are, and making some kind of a determination on them. For aviation, the determination we're typically making is a part serviceable? And the key word there being serviceable is, serviceable means it can be installed on an aircraft. Parts by themselves are not airworthy, right? The aircraft as a whole can be airworthy if it's made up of serviceable parts, or if you have the ability to defer non-serviceable parts, defer maintenance on non-serviceable parts. But ultimately, that's kind of the real difference. You really don't see it. It's not going to be anything too cut and dry. People aren't going to be, well, NDT and NDE are very, very different. No, NDE is kind of an extension. Non-destructive evaluation is an extension of testing and inspection. So when we're doing that, we're going to, the whole purpose of this, of testing, is to find flaws. We want to find flaws that aren't necessarily visible to the naked eye. When you do your detailed visual inspection, most of the time, if you can see flaws from a visual inspection, by that point, if it's a part that's going to need NDT, by the point that they're visible, it's definitely going to cause the part to be not serviceable. Right? If your NDT requires you to find a crack that's not visible to the naked eye, and you can see a crack that is visible to the naked eye, that's probably bigger than than the ones that are too small to see. So that part's not going to be serviceable at that point. But when we're doing NDT, we can get 3 different types of indication. So the ones we're looking for, the ones that are critical, are known as real or relevant indications. And this is that crack. This is the corrosion. This is the wear. This is what we're looking for and trying to make sure there's a. Now, just because we find a relevant or a real flaw does not mean the part's not serviceable. There are often cases where we can have, parts don't have to be in perfect condition and still be considered serviceable. Okay, example that we had to do regularly, we had to do dye penetrant inspection on our turbine cases on our engines. They were prone to cracking at the 3 o'clock and 9 o'clock positions, the 2 sides. They were allowed to have cracks of a certain size. The cracks, they were roughly, they could be up to about 2 inches long. Now they're so narrow you can't see them with the naked eye, but they can be up to about 2 inches long. The other determination is how quickly they were growing. So we would do these dye penetrant inspections. We would actually find cracks more often than not, but most of the time they were little, 1/4 inch, 1/2 inch, right? And that was okay. GE, the manufacturer of the engine, said that's okay. They weren't allowing gas to escape. They weren't anything of that. And they weren't big enough that they were at a point where they were afraid that the turbine case was going to come apart. But they were there. And so we would perform an inspection. This was a reoccurring. Once they found out that there was this cracking condition, we would perform that inspection and we would note how long it was, how big the crack was. And then we would have to go back on a regular basis. Again, it was based on flight hours, because engine hours. I don't remember the exact number. I'd have to get the whole procedure in front of me, and I don't have it. But after so many hours, we would check it again. And we would compare how long was the crack, say it was 1,000 hours later, how long was the crack 1,000 hours later compared to what it was 1,000 hours ago? We would also say, is the crack still less than 2 inches? So if the crack was less than 2 inches and it didn't grow more than, it was somewhere between 1/4 and 1/2 an inch during that time period, GE would say it's okay to keep running. But if that crack had grown an inch or more during that time period, the fear is that by the next inspection, it would exceed that 2-inch range. And so that would be a failure. So then that case, if it was more than 2 inches, or if it had grown over a certain amount in a period of time, now that case is no longer serviceable. That engine would have to be removed, and the turbine case would have to be changed. So real or relevant, we found a crack that's real or relevant. It doesn't always mean the part's not serviceable. You have to look at limits. The manufacturer or the part, the part manufacturer or the part overhaul, whoever has responsibility for the part or the aircraft, they're going to give you those limits. And then you, as the technician performing it, you're going to make that determination. And that's why we're going to have to document what we find. Now, there's 2 other types of flaws that we often would find, or we'll see. Indications, I should say. They're not flaws, but indications, really. So the next one is non-relevant. And these are indications that result from a known cause. This could be something like surface finish. If you have a rough surface, you're going to get a different type of, with different testing techniques, you're going to get different types of results on a rough surface versus a smooth surface. The dye penetrant example I was talking about, when you spray dye on a rough surface, it's going to hold on to more dye than a smooth surface. You're going to have a general layer of dye that you're not going to be able to clean off, right? It's harder to clean a rough surface. If you're doing something like eddy current, and with eddy current, we take a probe and we run it along the surface. If you're running it along a nice smooth surface, that probe's going to maintain contact and it's going to be good. But if you're moving it across a rough surface, and there's little tiny air gaps and stuff like that where the material in front of the probe is changing, you're going to get a different indication. You're going to get an indication that has some, it has some small variations in it, but what you're looking for is a larger variation indicating a crack, or indicating corrosion, or indicating thinning. Okay, so that's a non-relevant. It's due to the part, something to be expected, but not an indication of failure, of an impending failure. It can be because of a mold line. Everyone's seen parts where there's like a ridge on them, where the 2 pieces of the mold that made like a metal or a plastic part come together, right? That'll cause indications in some kinds of NDT. That's normal. That's part of the manufacturing process that gets left behind. It can be a hole. When you have a hole drilled in something, that's going to trap dye, or that's going to change how magnetic particles react to that area, because the magnetic field is going to be different when you magnetize a part. Or where you have like a 90 or some kind of a corner where 2 pieces come together, or there's some kind of a corner feature, inside or outside. So then the third one is a false indication. And a false indication is caused by some kind of a process error. This is typically caused by you. If you have a false indication, it's almost always caused by you, or it could be caused by a improperly produced procedure. There's some kind of an error in the procedure. But more often than not, if you have a procedure that's been published by a manufacturer, it's been tested, it meets industry standards. Usually those standards are from ASNT or ASN, or different, some of those different kind of bodies that do engineering and testing. Most of the time it's because of a cause that you made. This could be things like I have there, insufficient wash, overwash, dwell times. Those are all things that deal with dye penetrant. It can be because your machine is out of calibration. It can be because when you're moving a probe, you wobble it, and it causes an indication. It can be because of a fingerprint where you pick something up. Now, just because you have non-relevant indications, the big thing with non-relevant, you got to be careful. If you have areas where you're going to get non-relevant indications, what do you think that can do to real or relevant indications? Say you're looking for a crack down in a corner. What do you think a non-relevant indication that same quarter could do? Could be what? Could be hard to detect. It can hide a relevant indication. Same thing with a false indication. Okay? If you get a false indication somewhere on the part where you're not actually inspecting, do you think that causes an issue? Not really. Say you need to pick up a part and move it around. Well, ideally, you're going to grab it by an area not where you're inspecting. So you'll get fingerprints outside of your inspection area. They're not going to hurt anything. But if you get a fingerprint inside that inspection area, again, it could hide or it could smear or smudge or, cause some kind of a thing where you wouldn't see or where you might have a fault, where you might not pick up a relevant indication. So when you are doing your reports and when you're performing non-destructive testing, writing up your report for it, for any indications you find, you're going to need to classify them. Are they a relevant or a real indication? Are they a non-relevant? And are they a false indication? I can tell you on just about everything you do, you're going to be able to find at least 2 of these, if not all 3. Okay, you're learning. You're probably going to put a fingerprint on it. Okay, most parts are not perfectly uniform, right? They're funny shapes. They're different textures. So there's going to be non-relevant indications. So these 3 types of indications need to be classified when you do your reports. Okay, so those are our 3 flaw categories. The next thing we're going to look at is the materials that parts are made out of. Materials can affect what kind of tests you can perform. Materials can affect how those tests act when they're performed on them. An ultrasonic test performed on metal is going to behave differently than an ultrasonic test performed on a composite. We'll get into why when we get into ultrasonic testing, but it has to deal with essentially metal is pretty uniform, right? So if you pass a sound wave, ultrasonic is sound waves, if you pass a sound wave through it, it's going to move through it pretty smoothly. But if you think about a composite where you've got all those layers of fiberglass together and then layers of resin kind of between them, that sound wave is going to pass from resin to fiberglass to resin to fiberglass to resin to fiberglass, right? It's going to change that sound wave every time it goes through one of those layers. So you have to keep that in mind when you're looking at what the parts are you're testing, what kind of tests you can do. So here, we're going to start with basic metallurgy, and we categorize metals into 2 main categories. I'm sure you've seen this before. I know we talked about it in Intro to Aviation with materials. But just a quick review, we have ferrous and non-ferrous. So ferrous are ones that contain iron, and they can be magnetized. Right? Non-ferrous cannot be magnetized. They typically don't contain any iron, or they don't contain enough, if they're an alloy, they don't contain enough iron that they can be magnetized. Then you get some that are kind of in the middle. So ferrous can be magnetized, pure iron, steel alloys that are primarily iron, but then have things like carbon, silicon, lithium, tin, copper, nitrogen, nickel. Those are all, nitrogen is just N. Those are all alloying elements, and those are going to change the ability to magnetize a part, how it hangs on to magnetism, how strong of a magnetic field it develops. Okay, but those can all be magnetized one way or another. So some tests rely on the ability to magnetize a part. Magnetic particle is the first one that comes to mind since magnetic's in the name. So you can use something like magnetic particle inspection on a ferrous part. Non-ferrous parts cannot be magnetized. Titanium, aluminum, brass, bronze. Okay, those can't be magnetized. They will not hold on to a magnetic field. So you cannot use something like magnetic particle inspection to test those non-ferrous parts because they won't magnetize, it just won't work. You have to have a magnetic field in the part in order for it to hang on to magnetic particles. So you have to adjust your methods based on what kind of material it is. And then, like I said, over here, iron is going to have a much stronger magnetic field than other alloys of steel, particularly stainless steel is kind of somewhere in the middle. Stainless steel normally can't be magnetized, but if you run enough current through it, it will form an electromagnetic. So you crank the current through it, as long as it can handle the amount of current. What happens when you run current through something? It does what? It gets magnetized, if it can be. If you run current through aluminum, brass, bronze, or titanium, it really doesn't do anything. What else does running current through a metal do? No one's ever put a wire across a battery? Stuck a fork in an outlet? What happens? It gets hot. So it's a balance between what's the most current I can run before I cause damage to my part by overheating it. That damage can be melting it to the extreme end, or even just heating up certain parts. Remember, we use heat for treatment, heat treatment. right? If you heat a part, it could change the properties of the part. So we got to keep that kind of thing in mind when we're deciding. So stainless steel, we can run a ton of current through it, but if it gets so hot that it causes the tempering or the heat treating to change, now your part is no longer, your part becomes worthless at that point. So usually we can get enough field if it's a heavy duty enough part that it's not a big deal. So all metals, though, are electrically conductive. That's what all these share. So in these cases, we can run currents through them, which means we can use things like eddy current inspection or eddy current testing because we can run a current through it. Okay. With any of these metal parts, you have to take into account the fabrication technique, and this ties back into those, particularly those non-relevant indications. Or if your real indications could potentially be hidden, or you could get a false real indication. You see something that looks like a line or a crack, but it's really a line left behind by the machining process. So just a quick review, casting, little liquid metals poured in a mold. It typically has a rough surface. Okay. Forging, cold or hot metal, not liquid, it's still in a solid form, but cold or hot metal is forced into a shape by pressure. Okay. The metal flows inside of a die into a shape. Again, these typically rough forgings have a rough surface. In fact, last time on Tuesday I brought that gear in here. That was a rough forging. That had just come out of a forging die. It was cleaned, but it was rough. It hadn't been machined. Extrusion, again, taking a still solid metal. It can be hot or cold. You can do cold extrusion or hot. And when you're talking hot with like steel, we're talking like 1400 degree hot. Cold is room temperature. Okay. There's also warm forging that's somewhere in the middle, 700 degrees or so. But we take metal and we force it through a die. This is that thing, the example I use, and I really should just bring in Play-Doh, but you shove the Play-Doh into the little lever thing and it's got like the star thing on the front. It creates a long snake that looks like a star, a long snake that looks like a worm. And for those that maybe played with those things, that is extrusion. You're extruding Play-Doh in that case. So that we can do the same thing with metal. Rolling is forcing, again, hot or cold metal between two rollers to force it into shape. Now, what do you use? What do you guys see most often that's rolled here? Your sheet metal, okay? You can also roll shapes. Okay, the rollers don't necessarily have to be big flat rollers. They can be different shapes. So if you've ever seen like, you can make like seat tracks, like an I shape. You can have a couple rollers that kind of fit into those different things, right? So it doesn't have to be sheet metal. The most common is sheet metal, but you can roll other parts. It's different from extrusion in that you're going through a roller, whereas extrusion, you're just forcing it through a fixed shape die, not a set of rollers. They do a similar thing. They both cause the metal, forging, extrusion, rolling, all force the metal to flow, a still solid metal to flow. They create very, very strong parts. Casting, the metal is not quite as strong, okay? But it's a lot easier to do, okay? Liquid metal flows better than solid metal. It takes less pressure. You don't have any pressure involved. Machining is then we can take those parts, and typically they're a part that's been either cast, forged, extruded, rolled, or sintered, and we cut away material. This is where we take that rough gear that I brought in, and we remove that rough surface to leave behind nice smooth gear teeth so it doesn't chew up the other gear that's meshed into it. This is where we take a solid piece of metal and we bore a hole down the middle of it. This is where we take a screw and cut threads into it. Okay, those are all machining processes. Cutting, grinding, shaping, where we're removing some amount of metal. Sintering is or also known as metal fusion, is we take powdered metal and we put it under high pressure, high heat, not enough to melt it, but just before it melts, if you take a metal powder with enough pressure and heat it up just before the melting part, it actually fuses together, but it's still individual grains of metal. Okay. It's easy, it's a very inexpensive process, but the metal is very weak. It doesn't make particularly strong parts. But they can also be very lightweight depending on how it's made. They can be a lighter weight. Okay. And then additive manufacturing, most people know it as 3D printing. This can be done with metals. There are companies doing metals. Right now, majority of 3D printing for metals is for prototyping. It's not up to scale where you'll see. But in aviation, we often have parts that we don't have, aviation doesn't have the volume of parts like we do in something like automotive, right? There aren't nearly as many airplanes out there as there are cars. So they can make a die and forge or extrude or cast parts, but additive manufacturing, you don't have to have a die because you have essentially a print head. And so if you have low volume parts, so aviation is one of the first places that you're probably going to see more and more 3D printed parts, because it makes sense to do that rather than having to make an expensive die. The die is the thing that the steel or metal gets formed in, aluminum, titanium, they can all be formed by dies. That's the hollow shape that it's filled into. But if you're only going to run off 500 parts instead of 50,000 parts, additive manufacturing, 3D printing may make more sense. Right now, they're not as strong as things like forging, extrusion, rolling, and forging, extrusion, and rolling, which are the three that make really strong parts. That's the limit there. So many objects, though, are manufactured by some combination of these. Okay? And the reason we talk about them is these are going to all act different when you apply a given NDT, non-destructive test, to them. Right? Again, like I said, a smooth surface, a machined smooth surface versus a rough surface that came straight out of a casting, a forging, a rolling, right, are gonna react differently when they're tested. Okay? A sintered part where it's fused metal powders, you'll pick up that grain structure when you're performing NDT on it versus cast, forged, extruded, rolled, where it's a more homogeneous metal, right? So they're going to react differently. So you got to keep that in mind when if you're ever designing tests for these, if you get to the level where you're designing tests, or while you're performing tests, what kind of an indication am I going to see? Because that goes back to all of these can cause different non-relevant indications. And you don't want to confuse a non-relevant indication for a real or relevant indication. That means you're throwing away parts that don't need to be thrown away. It's a waste of money and time. Okay. Other things that we'll test, non-metallic materials. For the most part, what's used in aviation are types of polymers and plastics. Okay, and these are roughly, again, two categories here. Non-reinforced or coherent materials. My water bottle, for instance. Okay, plastic, but there's no like fiber reinforcing or anything in it. Okay. Compared to composites or non-coherent materials. So with plastics, we have 7 basic types. You've probably seen some of these or heard some of these abbreviations before. Things like polyethylene, high-density polyethylene, polyvinyl chloride, PVC, that's what a lot of your like plastic pipes are made out of. LDEPE, low-density polyethylene, that's what's coated on the inside of like a tin can. HDPE, high-density polyethylene, that's your milk cartons and stuff like that. Polystyrene, polystyrene foam is technically a plastic. And then people have heard of like BPA, water bottles like this used to be made out of BPA. They've since changed it. I don't even know what this is made out of at this point. It says BPA free, but other than that, I have no idea. And there's all kinds of other, even things like Teflon is technically in a plastic category and that kind of thing. So those are homogeneous. That's going to act different than a non-homogeneous or non-coherent material like I was talking about earlier, where sound waves, for instance, are going to travel much differently through this homogeneous material than they are through a composite where there's a bunch of different materials all kind of next to it, bumping up against each other. So your composites, non-coherent materials, generally speaking, the technical term we hear is RFP FRP, fiber reinforced plastics, where the fibers encapsulate inside a plastic material. Have you done fiberglass or carbon fiber layups at this point? Yeah, okay, so you know what I'm talking about there. But you'll hear these, and in aviation, they like to use the technical terms for these. So glass fiber reinforced plastic, GFRP, is the acronym you'll see, which is fiberglass. Carbon fiber reinforced plastic, carbon fiber. Aramid fiber reinforced plastic. The most common one you've heard of is Kevlar. Kevlar is I can't remember if it's 3M or DuPont. Who owns that trademark? One of the two big chemical companies. Is it DuPont that owns Kevlar? But aramid fiber is the general class. Other companies do make aramid fibers. It's just everyone refers to it as Kevlar, even though it's it's kind of like Kleenex versus tissue, right? Kleenex is Kimberly-Clark Corporation, but everyone calls tissues Kleenex anyways. Same thing here. Laminate, so those are where the plastic itself, where the fibers are embedded in the plastic. That's what you're making when you're making like a layup, or sorry, a single layer layup, I should say. They also can be, they don't have to be a mat. Like you've all used the woven mats, right? You can have a plastic where there's just like fibers embedded in it. Like they basically take a canister with a bunch of loose fibers and drop it into the liquid plastic, whether it's melted plastic or whether it's an epoxy before it cures. Epoxy, once it cures, is a plastic, by the way. It's a form of plastic. It's a polymer. So, it can be you're putting that on a fiberglass mat to make some kind of a sheet shape or some kind of a formed shape, or it can be a blob with fiber mixed into it. And it can be very thin, or it can be really thick like peanut butter. You can form it. Okay. So either way, they're all fiber reinforced. And there are some, occasionally you will get an object you might see around your house that has a fiber reinforced plastic. You can sometimes see those chopped fibers in it if you know what you're looking for. Laminate materials are if we oftentimes take multiple layers and put them together. You've done a laminate, you've done a layup. What did you all do for your project so far in structures? Did you do the square with the layers and the honeycomb in it, right? So now we're getting into laminate materials, the layers and materials bonded together. So it's fiber reinforced plastic sheets, right? It can be metallic sheets. You can actually have metal composites. The Saab 340s I worked on used a metal composite skin. The skin was not a single layer of metal, but rather a couple layers of thin layers of aluminum that were bonded together. And then honeycombs, like fiber metallic honeycombs. You all use fiber honeycomb, right? Almost looks like a papery honeycomb, right? But they make aluminum versions and titanium versions of that as well. Often used on engines and stuff like that. The last one is technically wood and fabric structures are a form of composite. Wood by its own, like just wood that's grown, is a composite. Cellulose layers and things are, they're bonded together and all that. Fabric is the fabric and the dope create a composite structure. It's still somewhat flexible, right? They don't have to be rigid, but it is a composite. So you got to keep these things in mind. Different materials and different ways of constructing them are going to cause differences in how your non-destructive testing reacts. So these also can be are created in several ways. So have you done a mold yet for fiberglass or carbon fiber? Or is that what you're going to do in advanced structures now? You've seen the stealth fighters, right, that everyone makes, right? You're going to use a mold you're going to set your carbon fiber into a mold to create that stealth fighter shape. Okay. You can also use things like just with plastic, right? Plastic has to be molded into a shape to create things. So compression molding, just forcing the plastic in. Injection, you have a mold and you shoot liquid in. Legos are injection molded. Okay. Rotational molding, you take a bunch of plastic pellets, you put them inside of a mold. That mold gets hot and it rotates, and so that plastic coats the whole inside surface, leaving something hollow, like a kayak. That's how like plastic kayaks were made. I used to sell kayaks when I was in college, and they were all it's called rotomolded high density polyethylene. Basically a fancy milk carton. They charge $1,000 for them. Yeah. They could make frisbees. So probably, I'm sure, I know they do this kind of stuff. Blow molding is something like this water bottle, I'm guessing is a blow molded part. They have a die that goes around the outside, plastic's put in, and then air pressure is put in the middle, and it forces that plastic out to the sides. Maybe roto molded, I don't know. Yeah, those are blow molded pop bottles, 2 liter pop bottle. It starts as a real skinny little thing, and they put it inside of a female mold, and then they inject air in the middle of it. They heat it up where it's not melted, it's just soft, and they stretch it out and blow it up like a balloon, right? So those are blow molded. Extrusion, warm plastic can be forced through a die to produce long continuous shapes. If it's long, skinny, or flat, it's possibly extruded. Machining, plastic can be machined. You cut away material. Again, it's going to be some kind of other part that then has material, a larger object that has material cut away. Although plastics, you can get pretty smooth surfaces even in the molding process. Additive manufacturing. People are more familiar with plastic additive manufacturing. This is your 3D printers you could have at home. 3D printers that we have over in the sim, or not the sim building, well, it was the sim building. Where the Seminoles are stored, there's a couple 3D printers over there. Engineering campus, design, school of design all have 3D printers. Forming, taking sheets and putting them against warming them up and putting them against the die, or using a vacuum to hold them in place. Kind of the opposite of blow molding. And so again, most of these objects are going to use some combination of these things. Okay. So when we're selecting our methods, we've got a lot of things we got to keep in mind in order to test our various parts. So the first one on the list here is technical capability. What's technical capability? What's the big variable there? Are you technically capable of performing any of the methods that I've discussed besides detailed visual inspection at this point? Probably not. None of you have practiced them. None of you have tried them. Maybe someone's done one somewhere. Maybe borescopes. Maybe you've used the scope a little bit. So, but I doubt most of you have technical capability to perform liquid penetrant, mag particle, eddy current, ultrasound, X-ray, right? So technical capability is that. The other part of that is the equipment that goes along with it, right? I don't have an eddy current tester at home. Got 3 or 4 of them here, but I don't have any at home, right? So your organization has to have it. Sometimes there's more than one way to test a part. So oftentimes you can use dye penetrant or eddy current, for instance. Dye penetrant's a lot cheaper, easier to obtain, easier to train. It's not quite as good at finding very, very small cracks. And it can't be really used on plastics, whereas ultrasound could be used on plastic, for instance. What's the expected flaw? What are you trying to find? Different techniques are designed to find different flaws. Some techniques are better at finding surface flaws. Other techniques have the capability of finding subsurface flaws. Okay? On a metal part, eddy current testing is great for surface flaws. It can't do subsurface very well. Ultrasound can do subsurface flaws, but it can't do surface flaws very well. We'll talk about the limitations and why that's the case for all the different methods, but you got to take that into account. Criticality. How small does the flaw have to be for you to find it? Or how small, let's see. What's the biggest the flaw can be when you find it before it becomes a problem? That makes sense? So if you have to find a part, if you can find a flaw when it's visible and it's still considered serviceable up to the point where you can see it, why would you bother doing these more expensive, more involved, more technically complex processes if you can just wait until it's visibly worn, or you can measure it with just a pair of calipers or something, right? So the criticality takes that, and cost and time play into that, right? Most of these methods are going to be more expensive than a visual inspection. Most of them are going to be more expensive than you pulling out a set of calipers. Type and size of part. Our mag particle bench down there can hold a part about yay long. I can't do a full wing spar on the mag particle bench. Right? I have to do that on wing. Probably don't want to try to remove the wing spar from the plane in order to do a mag particle on it. So I need something where I can test it built into the plane. I don't want to have to strip the skin off the plane to look for cracks. At that point, I may as well just reskin the airplane. So I need to have something that's portable that I can take out there. So type and size of part, whereas smaller parts, I might be able to send them out to somewhere like Duncan that can do 100 of them right in one batch. Boom, 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 one after another. Right? Rather than buying a mag particle machine in my company, my small GA shop, right, to test the bolts that hold the ailerons on, And I'm probably going to send something like that out unless I'm doing it all the time. Environmental conditions. A day like today would be very hard to do thermographic inspection of an aircraft. Because everywhere you get a piece of snow on the airplane that melts into water, you're going to get a false indication from a cold spot. It'd be really hard to find a delamination. You use thermography to find things like delamination and water ingress in composite materials. Well, water on the surface looks a lot like water that's in the inside too. It's kind of hard to tell them apart. So if you've got a bunch of snow and water on an airplane, you probably can't use thermographic inspection today outdoors. And then the type of materials I mentioned. Is it something that can be, is it ferromagnetic? Is it conductive? Is it homogeneous? Is it not homogeneous? Is it big enough to clamp into the mag particle bench? Is it small enough that I can handle it and be able to do it on a bench? Or is it so big that I need to go out and use portable equipment on it? Right? Again, that all ties into type of material, size of material, all that. Okay. Questions on materials, kind of introduction to what, where, when, why, how?